Hello and welcome to everyone in Physics Fire. Today we are going to do the third part of Class 12, Current Electricity. So yet we had done the basics of current, how current flows and all. And then we had done about drift velocity. We did few numericals on drift velocity. Today's class, we are going to see that the behavior of a conductor and a semiconductor with respect to temperature. Then we will write the temperature dependence equation, and then we are going to do few sums related to that. And the last topic will be Ohm's law and its limitation. Actually, we finished Ohm's law, so we will do here what limitation of Ohm's law. Let's start now. So let's revise first whatever the formulas at least we had done, so that we can make a short note kind of thing. First, we had done I is equal to Q by T, right? Q is equal to what? NE by T, right? Then we had done I average, right? I average is equal to what? Q final. Q final minus of what? Q initial by T, right? Then we had done I instantaneous. That is what? dq by dt, right? Next, we had done the drift velocity. Drift velocity is equal to what? E tau by what? M. Tau is what here? Relaxation time. E is what here? Charge. Capital E is what? Electric field. Vd is what? Drift velocity. Even we had done sigma E by En, no? That is what we had done. One more formula we had done, no, of drift velocity. Sigma E by En. That also. Drift velocity can be written, suppose you are taking a electron is going from here to here. Path difference is lambda and time is tau. So drift velocity, we can say displacement by time. That also we can say. Fine. We had done after that the relation between current and drift velocity, that is I is equal to NEA VD, right? Then we had done V is equal to IR, right? But R is equal to ML by NE square tau into area. Then we had done rho. Rho is equal to M by NE square tau, right? Then we had done current density, that is denoted by what? J. J is equal to what? I by A. J is equal to sigma E also. That we say Ohm's law in a vector form, right? Mobility, then we had done drift velocity per unit electric field. So these are the formulas that we had done yet in current electricity. In today's class, we are going to do what? Some of the questions are not, we'll start with the question actually. We'll start temperature dependence of resistance and resistivity. Let's see temperature dependence of resistance and what? Resistivity. Temperature dependence of resistance and resistivity. Okay, fine. That you guys write the topic. So the first thing, if you see here, that we are going to see here, what? R resistance formula. R is equal to M by N E square tau into area into L. Guys, here M is what here? Mass of electron. Tau is what here? Relaxation time. Area is what? Cross section area of the conductor. L is what? Length of the conductor. So we are going to see that if you increase temperature in a conductor, then the resistance will increase or decrease. What will happen to the resistance and resistivity? And you'll see the graph also. So let's see if you increase temperature. If you are going to increase temperature, then obviously at room temperature around 30-32 degrees Celsius, n number of collisions are there. And due to that collision, the velocity of the particle, it is 10 to the power 4 meter per second. It's a huge, right? So that much velocity is there without what? With just with what? The room temperature. If you give more temperature, then of course n number of collisions will be there. So we can say if you increase temperature in a conductor, right, and what is going to happen? More vibrations of electron, more collisions, right? Ultimately, what happens here? I'm giving an example. Suppose a big apartment is there, many homes. Let's consider 100 homes are there, 200 homes are there inside that apartment. A big playground is also there. Kids like you guys, who is not, you guys are good only. The kids who is not obeying their parents, so those kids are what? Kick them out, like parents kick them out from home. So what will happen? They will come here, the playground, and they will play. But the problem is what? Frequently, the parents are coming outside to see what they are doing. So they cannot play properly. Why? Because in between, they will have to hide somewhere, right? It means what will happen? The time, the collisions will happen again and again. Means what? Same in atoms also, if you will see, in a conductor also, if you will see, the relaxation time when you will increase temperature, then what will happen? Relaxation time will increase. So we can say here, increasing temperature, tau will decrease. If tau will decrease, then resistance will increase. Simple. Resistance will increase. Resistivity will what? Also increase. Sigma will decrease. Current will decrease. That's it, right? So the graph, if you will see, that is what? Resistance and rho graph versus time. The graph is what? Is going to increase on increasing temperature. Got it? So this is the case on the conductor. If you will say a semiconductor, right? If you will take a semiconductor, it is completely different now. Let's see how. Semiconductor, if you will see, then we can say here again the same formula. R is equal to ml by ne square tau into area. By increasing temperature here, the main thing which is going to affect is n increases. What will happen here? N will increase. N will increase. By increasing temperature, n will increase. What is n? Number of charge gauges. So if you will see in a semiconductor, there are two types of charges are there. What are those? Holes and electrons there. So both will increase. If both will increase in a semiconductor, if temperature increases, number of charges also increases, then what will happen? Resistance will decrease. If resistance will decrease, rho will also decrease. Sigma will increase. Current will what? Increase. So on increasing temperature in semiconductor, current increases. So rho and sigma and resistance versus time, it decreases with respect to time. So that is about what? A semiconductor and a conductor on increasing temperature, how it will affect, that we learn. Now we are going to see in a conductor, if you are increasing temperature, then how much temperature increase, how much resistance increase, that we are going to see. So they had done experimentally, we observed by increasing temperature. Suppose any conductor is there. Let's consider this is the conductor. We increase the temperature, right? Before the temperature is T, and the resistance was what? Well, let me draw it properly again. Let's consider the temperature was T, right? And resistance was R. We subjected to heat and we got like this resistance in a temperature increase to dt. So the temperature was before T. Now the temperature is T plus dt. Resistance, you know what happened? R plus dr. So by increasing temperature, resistance also increased, temperature also increased. So we can say change in resistance depends upon what? The dt, of course, the what? Resistance, right? More resistance will be there, then only there will be more change. To remove this, we'll introduce a constant. It looks like similar only, that is what? Alpha, temperature of what? A coefficient of thermal resistance. So dr is equal to what is that? Alpha r dt, alpha r dt. Okay, so now what we are going to do, what is that? Alpha r dt, coefficient of thermal resistivity, the resistance, that we can say coefficient of thermal resistance. Right? Okay. So now what we are doing, we are like, it's not for one dr, we are increasing too much temperature, so too much of resistance will also increase. So we can say now the equation is we'll have to integrate it, not dr, we want to find actually r. So we can say dr integration from where? Initial resistance to final resistance, to what? Final resistance, that is equal to increase alpha r dt, alpha r dt, that is what? T t0 to what? T final, right? Okay, now we'll have to integrate. Dr integration is what? R only, so we can say directly r t rf minus of what? R naught is equal to alpha r is constant, so we can say T final minus of T naught. All right, so rf is equal to r naught, this is also r naught. All right, r naught into what? 1 plus alpha T final, T initial, that we took what? Delta T. So this is the equation for what? This is the equation for, okay, I didn't wrote in a straight line, fine, anyway, you guys understood. This is the equation for what? R, it's we did a major mistake. This is RF, guys, RF, right? That's fine. We can say rho also, rho f is equal to what? R naught into what? 1 plus alpha delta T. That rho naught, not R naught. Yes, so this equation we can write. For semiconductors also, if you will see, that also varies. Let's see how it varies. Okay, let's write the values of alpha. Alpha for conductor, alpha for what? Conductor is positive, is what? Positive. Alpha for semiconductor is negative. Alpha for insulator is 0. Nearly equal to what? 0. Yes. Now let's see, for on increasing temperature on semiconductor, what happens. So for semiconductors, if you increase the temperature, by increasing temperature, number of ends, no, here increase exponentially. Why like that? Because we know that here charge carriers is not only due to electron, it's due to what? Holes also. So we can say now that is going to be nt is equal to n naught, right? Nt is equal to n naught e to the power minus eg divided by kBT. This is what Eg is energy gap. Whenever in semiconductor conduction will happen, then from valence it will go to what? Conduction. Valence band to conduction band. So the gap between them is known as what? Energy gap. What is that? If you see, I'll tell you, that is what? Eg. Valence band and what? Conduction band. Fine. So we can say now the equation is like this. Fine. This is what? Boltzmann constant, and this is what? Energy gap. Same thing, we can say if number of n will increase huge, right? So what will happen? Sigma will increase, right? If n will increase suddenly, then what? Rho will decrease, sigma will increase. In the form of rho, if you want to write, then we can say 1 by n. So 1 by rho into what? In temperature increasing, so 1 by rho naught is rho naught in rho naught e to the power minus of Eg by kBT by what? kBT. Fine. So we can say rho t, right? Directly I wrote rho t is equal to rho naught t e to the power Eg minus of kBT. Yes. So this is the equation for what? Semiconductor. This is not for board, but in mains and NEET they asked this question. Direct question was there. Fine. After that we should know what? 1-2 questions. Let's do those questions on that that numerical temperature dependence equation. The resistance of a tungsten filament at 50 degrees Celsius is 133 ohm. What will be its resistance at 500 ohm? Right? Resistance we are supposed to find. Final resistance. Temperature coefficient is given. So write to equation. We know the simple equation is what here? R, right? RT is equal to R naught into 1 plus alpha delta T. Yes. So RT, let's take first is what? R. It is 150 degree. 150 degrees Celsius, right, is equal to what? R naught into 1 plus alpha. Alpha is given. No, okay, leave it. 1 alpha is 0.045 into delta T is going to be what? T minus of 0, so 100 degrees Celsius. No, 150 degrees Celsius. No. And resistance at how much? 500 degrees Celsius we want to find. R naught into 1 plus 0.045 into what? 500 degrees Celsius. So from here, if you divide 1 by 2, R naught cancel out. Now R 150 is given here, 133 ohm. So all, if you will solve it, then you are going to get what? R, let's consider like it is, you take it up, R 500 divided by 133 is 1 plus 0.045 into 500 divided by 1 plus 0.045 into 150. So that if you will solve, finally you will get as RT, R500 is equal to 258 ohm. That is the answer you are going to get from here. Hope so. It's easy question. You guys understood it. Once you try by yourself, then you do this. Let's see. The second question says that what? The resistance of a platinum wire of platinum resistance thermometer at ice point is 5 ohm and at a steam point is 5.23 ohm. When the thermometer is inserted in a hot bath, the resistance of platinum wire is this. Calculate temperature here. We are supposed to find what here? Temperature. So we can do one thing here. The equations remains the same here. RT, right? RT, we can say minus of R naught. I took the R naught side. And then we can say what? R naught into what? Alpha delta T. This is the first equation. Second equation, R100 minus of again R naught is equal to R naught into alpha T. T is how much here? 100 degrees Celsius. So I wrote that. So this is the equation number 2. Let's divide the first divided by 2, 1 divided by 2, 1 divided by 2. So RT minus of R naught divided by R100 minus of what? R naught is equal to alpha T. These values will get cancelled out. So T by 100, right? So now RT value or the thermal resistance RT temperature this what is that? R naught is 5.23. 5.23 minus of 5 divided by 5.795 minus of what? 5 is equal to 1 by 100 is equal to what? 1 by T by 100, not 1 by 100. Then everything will become waste, right? So T, if you will solve from here, you are going to get what? Around 345. 345 60.65 degrees Celsius. Yes, so that is the what the answer you will get from here. Fine. It's again the easy question. 2 equation I make and then we wrote the answer. Fine. Now what we are going to see, we learned Ohm's law already. We are going to see the limitation of Ohm's law. Limitation of what? Limitation of Ohm's law. Yes, limitation of Ohm's law, right? Limitation of Ohm's law, if you will see, this law is not a fundamental law, right? It is not a fundamental law of nature. It depends upon the material. And the material depends upon what? Temperature, some conditions. So it is obeyed by the substance under certain conditions. So let me write it. It is obeyed. It is obeyed by many substance under certain condition. That certain condition can be anything, but we know that temperature and all, right? Fine. Because it is not a fundamental law. For a conductor, if you will take for a pure conductor or pure metal, ohmic conductor I and V, the graph will be like this. For non-ohmic, so we define that like ohmic and non-ohmic conductor. Non-ohmic conductor, suppose when a large current are passed, when what? When a large current is passed, when a large current is passed, when what? Large current is passed through a conductor, through a conductor, it gets heated up, right? It gets what? It gets heated up. It gets heated up, right? Due to that, what will happen? If you will see the graph will be wait, I'll tell. It was supposed to go like this. I'll draw by a thick pen like this, but it will go like this, right? So this will be the original I and V, or V and I, V and I curve, right? For a PN junction diode, That is also what non-ohmic curve. So it is going to be like this. For a gallium arsenide, non-ohmic curves I'm drawing only. Gallium arsenide. In this, all no currents will be in what milliampere. Voltage current will be in what milliampere, and then here voltage. Hope so you guys got it. Limitation of what? Ohm's law. Next class is going to be really interesting. There about we will learn about what? Resistance, combination of resistance. I believe till here you guys understood, right? If you understood properly, then like it, and then as well as what? Subscribe. We'll see in the next class.